Dear students, in this video we are going to see how every integral domain can be embedded in a field. So for that, first we'll have the definition of embedding, or when do you say that a ring R can be embedded in a ring R prime. So the definition says this: a ring R can be embedded in a ring R prime if there is an isomorphism of this ring R into another ring R prime. Now suppose R and R prime, they have unit elements, say 1 and 1 prime respectively, then this isomorphism will take 1 to 1 prime, and this R prime is called an overring or extension of R. So when we can call our R prime as overring or extension of R, if R can be embedded or embedded in R prime. Now, see, we keep saying that all integers can be thought of as rational numbers. How do we say that? So for that only we have this theorem, and in the same way, constants can be thought of as polynomials. So we say so. So how is it possible? So which result, a theorem which tells us that even the constants can be thought of as polynomial. So it is this concept that embedding that help us to conclude such statements. So now we'll go to this theorem. Every integral domain can be embedded in a field. So you're given only integral domain. From that, you need to construct a field, and then you have to embed this integral domain into that. So we'll first see the outline of the proof. See, we are remember we are given only integral domain D. D is going to be considered as an integral domain, right? From D, we are going to construct, or rather, we are going to introduce one collection M. So, what is that M? Script M. That will be explained in the proof. So, just the outline alone that we are going to see now. So we are going to introduce one set M. Actually, it is collection of all ordered pairs AB, where AB are all elements of D. D is the given integral domain. This is the given integral domain, and we must mention that our B is a non-zero. B should be a non-zero element in D. So we are going to first introduce this collection M, script M, and we are going to define a relation tilde on M. So if you take two elements, say AB and CD, we are going to relate these two. How that relation is going to be defined? It is A into D is equal to B into C. AD is equal to BC. So whenever we have AD is equal to BC, then we can say that this ordered pair AB is related to CD. And whenever this is true, we must have AD equal to BC. So we are going to define a relation tilde on our script M, and then show that script M, that relation is an equivalence relation. We are going to show that it is an equivalence relation. And then whenever we have an equivalence relation, we can talk about the equivalence class. So the elements of script M are denoted as ordered pair AB, and the corresponding equivalence class, actually speaking, this is how we need to represent, but it is given in the text as this. So the equivalence classes, once we have equivalence relation, we can talk about equivalence classes. So you collect all the equivalence classes and call that collection to be this F. So F is introduced in this way. Your A and B are members of D, and your B not equal to 0. You must mention that B is non-zero. When you describe script M, you have to mention. When you describe F also, you must mention. So we introduce script M, and then we define a relation tilde on M, and show that that tilde is an equivalence relation. And once you have equivalence relation, you have equivalence classes. collect all the equivalence classes, call that collection as F, and show that this F is a field. So you given a collection F, we are going to define addition and multiplication on F. So having got this addition and multiplication, we need to check all the 11 axioms for this to be a field. Once that is checked, we can say that this F is a field. So we have got D, we have got F. Now our main proof is to embed D into F. So for that we need to define phi. Once you define this mapping phi from D to F, how it has to be defined or how it will be defined. Phi from D to F, we are going to have it as A being taken to A1. This equivalence class A1. And having got the definition of phi, we will show that this phi is one-to-one homomorphism. So that we can conclude from the definition that this D can be embedded in F. So this is the outline. So you are having only D. From D you are describing M, and then you define on M equivalence relation. Then with the help of equivalence relation, you will have equivalence clauses. That collection is denoted as F. Then prove that this F is a field. So and then you from between D and F define a mapping and show that is one-to-one homomorphism. So DMF, that is to be remembered. To prove this, DMF, D the given integral domain, M is you are going to describe it in this way, and then equivalence relation, all that are hidden. Just very brief outline, or as a mnemonic code you can remember DMF. So this is the outline of the proof. Now we'll go to the actual proof of this theorem. Now let D be the given integral domain. Describe your script M as collection of all ordered pair AB, where A, B are members of D with B non-zero. B non-zero is to be mentioned. Then you are going to define a relation tilde as this element AB and CD. Remember in this your B and D are non-zero. B and D are, both of them are non-zero. So you are going to define in this way. AD should be equal to BC. Like this the relation is defined. Now this relation is an equivalence relation on M. That is what we are going to first establish. And that's our first claim. So when you start like this, I mean when you give the proof of this claim, what is known about tilde, that is to be written again. So consider the relation tilde on script M defined this way. We shall name this as equation 1. Now reflexivity, symmetry and transitivity are to be established for this tilde to be an equivalence relation. First we'll see about reflexivity. You consider an element ordered per AB in script M. Now because your AB is equal to BA, this is because your whenever you have D to be an integral domain, it is a commutative ring without zero divisors. So whenever you are given A and B, the product AB, you can always write it as BA. And this how I can interpret AB is related to AB. Why? AB is equal to BA because D is commutative. Because D is commutative. So we have A dot B equal to B dot A, and therefore this is true. Because this is true, your relation is reflexive. So this proves the reflexivity. Because AB is related to itself, that is because of this, and this is because D is commutative. Now symmetry, for which you need to have two elements, say ordered per AB and CD from script M, we shall assume that AB is related to CD, which means AD equal to BC. So that is by 1. That is how the relation is defined. Now because D is commutative, you can rewrite BC as CB and AD as DA. Now this can be interpreted again by 1. This can be interpreted as CD related to AB. So that you'll have CB equal to DA. That is what we have here. So your element CD is related to AB, and that proves symmetry. Whenever A is related to B, B should be related to A. That is your symmetry. So here in this case, with these two elements, we are able to establish that. For transitivity, we need to have three elements. We have taken them to be A, B, C, D, and E, F from M. So we shall assume that AB is related to CD and CD is related to EF. So by 1, this means that AD is equal to BC. So that is what we have written. We shall name this as equation 2. And from here it is CF is equal to DE. So name that as 3. Now multiplying 2 by F, remember, see, whatever we have in the second place, they are all non-zero because they have been taken from script M. By the description of script M, your B should be non-zero, your D should be non-zero, and F also non-zero. So we are multiplying equation 2, this both sides by F. So that means ADF is equal to BCF. And multiply this by B. So that you have BCF equal to BDE. There is no need to say post multiplying, pre multiplying. The reason is all these are happening in D. D is commutative. In the case of commutative ring, there is no need to mention about pre multiplication or post multiplication. So just multiply, it's enough, right? And from here we have BCF being the same, ADF must be equal to BDE. So you have ADF is equal to BDE, and because D is commutative, we have DF being rewritten as FD, and BDE, and that is rewritten as BED. Now because D is non-zero, and your capital D is an integral domain. So how this we can rewrite AF minus BE into D is equal to 0 because D is non-zero. Here we have mentioned D is non-zero. So that means your AF must be equal to BE. So AF is equal to BE, which means um, your AB, you can even interpret, you can rewrite in this way. AF is equal to EB. So once you have this, you can now interpret this as A, B related to this, so that you have AF equal to BE. So AF BE only we have now, so it's correct only. So AF should be equal to BE according to 1. So this proves the transitivity. So the relation tilde is an equivalence relation on script M. So once you have equivalence relation, you can talk about the equivalence class. So we shall take actually speaking, for a given element A, this is how we denote the equivalence class. Here the elements are A, B. So its equivalence class, strictly speaking, should be given in this way. For the sake of simplicity, that is just denoted as this class AB. So let class A be the equivalence class of A in script M of this element AB. Now, see, in the due course, whenever we need to have the equivalence classes to be equal, it is enough we establish the elements are related. So under the relation defined earlier. So whenever, see, in the equivalence class results at the beginning, you would have learnt all this equivalence class results. We have, whenever A is related to B, we need to have the corresponding classes to be equal, and whenever the classes are equal, the elements must be related. This is one of the fundamental results on equivalence classes. So that is what is mentioned here. We know that if X is non-zero and suppose D has unit element say 1, then this concept, see, as such, this may not be used. Maybe later in the main proof we'll discuss about this, or rather we will use this. So otherwise, just the concept, because two equivalence clauses are equal means the elements must be related. Just check whether the elements are related. You have the element corresponding to this to be ax ordered pair axx, and this one to be ordered pair a1. Now this into this, ax into 1 must be equal to x into a. But ax into 1 is ax, and because d is commutative, you have to, I mean, you can write ax as xa. So these two are related. Because the elements are related, the corresponding equivalence clauses must be equal. Now, having got these equivalence clauses for all the elements present in script M, we collect the classes, equivalence classes, and call that collection to be F. So F is the collection of all this class AB, where A, B belong to D and B is non-zero. You can even just write like this, straight line, and instead of this where. So it can just be written this way: F is nothing but collection of all classes. Here you should not have ordered pair. Equivalence class only you need to write, such that A, B are members of T with B non-zero. Whether you describe your script M or F, remember this should be mentioned. Now this is the field that we need to we are searching for. So that means we have to define addition and multiplication for the elements of F. So how are we going to define? You consider two elements, say AB and CD. You define this addition in this way: AD plus BC, and then in the second place just multiply these two and write. See, if you feel that this is very difficult to remember, just compare, or rather recognize this AB as A by B and this one as C by D, so that you can have AD plus BC by BD. So this is known to us. So if you are not able to remember this, just have in your mind that roughly you can have this, and then put this one in the first place and this one in the second. And this one it's like component wise multiplication: AB into AC into this one, AC into BD. So multiplication is very simple. And now, having defined addition and multiplication, these are defined by us on F. So we need to prove that they are well defined. So the above defined addition and multiplication are well defined. Now, how are we going to prove well definedness? See, normally if we are given any function F from A to B, this is the general case we have. If you want to establish this F to be, it is defined in this way. Say, for example, F of A is equal to, say, some A square, or A or just B, right? So, for example, it is defined in this way. Say, we want to establish that this F is well defined. What we need to do, A is equal to, say, some A prime. Then now in the domain, two elements are equal means in the codomain the corresponding images should be equal. Only then we can say that this function F is well defined. So this is what we mean by well definedness, right? So here we know that every operation can be thought of as function. So here two elements you have. One is AB, the other one is CD. So when you assume that AB is equal to A prime B prime and CD is equal to C prime D prime, the operation addition is well defined, means AB plus CD should be equal to A prime B prime plus C prime D prime. So that is what we need to establish for plus and dot to be, I mean for addition to be well defined. In the same way for multiplication, instead of plus you will have dot. Now, having given AB to be equal to, I mean the class AB is equal to class A prime B prime, what does it mean? See, whenever two equivalence classes are equal, the corresponding elements are related. The corresponding elements are related. So that means ordered pair AB should be related to ordered pair A prime B prime. But by the definition of this relation tilde, this into this must be equal to this into this. So that is what is written here. AB prime is equal to BA prime. We shall name that as C patient 4, and the same way CD equal to C prime D prime implies that CD prime is equal to DC prime. Name that as 5. Now we prove that what I mentioned here. So this is what we are trying to prove. So that is same as proving. We know how addition is defined. This is how it is defined. AD plus BC, then the second place BD. And here A prime D prime plus B prime C prime, and then the second place B prime D prime. So this is what we need to prove. Now proving the, to prove that two equivalence classes are equal, we need to prove that the corresponding elements are related. So what is the corresponding element? This one, and it should be related to A prime D prime plus B prime C prime B prime D prime. So this is what we need to prove. So that is to prove that the elements are related. Now to prove that the elements are related means this into this must be equal to this into this. So AD plus BC we have written here into B prime D prime, this one should be equal to BD into A prime D prime plus B prime C prime. This is what we need to prove ultimately. So you consider LHS and using distributive law in D. D is an integral domain, so that means it's a ring first. So you have by distributive law AD into B prime D prime plus BC into B prime D prime. Now again by using commutativity in D, this is rewritten in this way: A B prime D D prime, and here B B prime C D prime. So using 4 and 5, what is 4? Here AB prime can be replaced by BA prime. So AB prime is replaced by BA prime, and 5 is CD prime is rewritten as DC prime. So CD prime is rewritten as DC prime. And in this again use commutativity and distributive law so that you can write this as BD can be taken out, A prime D prime plus B prime C prime. See, in each step you write the reason that how that step has come. So only then when you define later on your own any structure, then the verification will go correctly. So you have to reason out each and every step. So that is my RHS. What we have mentioned here, BD A prime D prime plus B prime C prime. That is our RHS. So addition is well defined. Now multiplication is well defined. So for that we need to prove this. A B C D should be equal to the equivalence class A prime B prime dot C prime D prime. So this is equivalent to proving that multiplication. We know how it is defined. It is component wise. So you have like this. This is what we are trying to prove. So that is to prove. So again, as before, classes are equal means the corresponding element AC BD must be related to A prime, C prime, B prime, D prime. So two elements in script M are related provided this into this is equal to this into this. So that is what is written. That is to prove that. So you consider LHS using commutativity in D under multiplication. You can rewrite this as A prime C D prime, and using 4 and 5 it is rewritten as BA prime into DC prime. Again, using commutativity in D, you have this, and that is your RHS. So dot is also well defined. Now we are going to prove that this F under plus n dot is a field. F is the collection of all equivalence classes, and how addition and multiplication are defined, and they are well defined. All that are shown earlier. Now we need to prove that this is a field, which means all the 11 axioms for F to be a field are to be established. So first one is closure property with respect to addition. So with respect to addition, see 11 axioms. What are the 11 axioms? Under addition, it should form a group. And similarly, under multiplication, it should form a group. So under addition, 5 axioms. Under multiplication, 5 axioms. What group? Abelian group. So under addition 5, under multiplication 5, and then distributive laws. So altogether 11 axioms. 11 axioms are to be checked. So you have first one, closure property. Now this one follows from claim to the first one, that is well definedness. So from that it tells that it is there in our capital F. And not only that, you have the second component should be non-zero for any element to be a member of F. And when we consider this, B is non-zero, D is non-zero. Once you consider them to be members of F, the second one should be non-zero. So that means BD should be non-zero. And it is well defined, and therefore closure holds. And associativity. For that, three elements need to be considered. So we shall take them as A, B, C, D, E, F. We'll have to just change the bracket and establish that. So you consider the LHS. Using addition in F, we have this AD plus BC into, and the second component BD you have, plus this one is retained as such. Now you treat this as A and this one as B and this one as C and D. C and D. So that AD plus BC. AD means AD plus BC, A. D means F, we have written. BC. B is this one, BD. BD. And then BC. B into D. B into D, that is all. B into D. So that means BD into F. So second one, there is no problem. As for the first one only, we need to remember this with this plus AD plus BC. AD plus BC. So this is what we have to prove. Even otherwise, as I said earlier, if you are unable to remember, use this way: A by B plus C by D. It will be AD plus BC by BD. But this is the notation that we keep using, so you cannot bring this one inside. So that is wrong. For your easy to remember, this can be used in the rough column. You have all this, but that should not be brought here inside the proof, because this notation is to be written throughout. Now AD plus BC into F plus BDE, AD plus BC, and the second one said earlier, there is no problem. BDF you have as such. Now using distributivity in D, you have ADF plus BCF plus this one retained, BDF as it is written. Now we simplify RHS. RHS is this one as retained as such, and this one, this with this, C with F. So AD plus BC. So CF plus DA comma this one as such df we have. So then now again using addition in f, this is written as this into this. So adf, and then this into this. So you have bcf, one step in between is skipped. BCF plus B into CF plus DE, that is BCF plus BDE. So this is what we have, and then the second one just to multiply these two and put it in the second place. So you have the same thing, ADF plus BCF plus BDE plus BDF here DFP, but because D is commutative, that and that will not pose any problem. So that is your LHS. Now existence of additive identity. See, you have any element in this one, that is in F to be this. We said already that it can be recognized as A by B. And to this, when you add 0 by B, where remember B not equal to 0, what you get is A by B itself. So this one act as the 0 element. You can even add like this, AB plus 0B. So what you get is this with this. So AD plus BC. B into 0 is 0. Then this one is B square. Right. Now this is AB, BB. Remember in this note we already said that AXX can be regarded as A1. So in the same way here, this is equivalent to AB because the elements BABB, AB, BB ordered pair is related to AB. Why? Because this into this, which is AB square, is same as B square A. So because this is true, this one is true. And because this one is true, as the elements are related, the equivalence classes must be the same. AB, BB must be equal to the equivalence class AB. So we can very well write this in this way. So this is the reason this ABB is same as AB. So you added with this 0B and you have got back this, which means this is identity element. For when whatever element that you consider, the second one should be non-zero. The second one should be non-zero. Now suppose I consider AB, and you know pretty well D is an element which is non-zero. We shall check whether 0D will act as identity element. So AB plus 0D, what does it give? It gives AD plus 0, then BD. Just now we said that this is same as AB. As though that you can cancel this and write, but it is not so. It looks as though that we cancel it and write it. So that means this doubt will arise. Do we have 0B, 0D, and whenever suppose I have F to be non-zero, then 0F. Are there so many 0 elements present in F? But we know that 0 element, that is additive identity, should be unique. You cannot have too many additive identities. So then how come you say that these are all identity elements, but identity element with regard to addition or multiplication should be unique? Now as classes they are equal. As classes they are equal. Just check it. 0B should be related to 0D. Is it not? 0 into D is same as B into 0. 0 equals 0. So because this is true, this is true, this is true. And because this is true, this is true. And whatever you consider in the same way, this. So even though you say that 0B, 0D, 0F and so on are all 0 elements present in F, they are all equal as equivalence classes. Now, existence of additive identity. Now, you consider any element AB for which minus A comma B will act as the additive inverse. So that even can be checked in the same way. And then commutativity with respect to plus, you have to have AB plus CD should be same as CD plus AB. And you consider LHS, the addition is defined in this way. So this is the definition of addition. So using that you are writing it. And your addition under addition, this is commutative. So you rewrite in this way. Again under multiplication also it is commutative. So you have this step, and this is nothing but just see that CB plus DA, and then second place DB. So you have this. So this is nothing but the sum of these two. So that is your RHS. That is your RHS. So commutativity with respect to plus is also established. Then closure with respect to dot follows from second subdivision of claim 2, which you have already established. Then associativity, it is the same way that what we had in the case of addition we need to have. We'll have to change the bracket and establish this. So if you consider LHS, you have AC dot EF, and it is something like component wise, So ACE comma BDF, and RHS you consider separately. CE DF, when you multiply component wise ACE, this is ACE, this is ACE, ACE BDF. Second is written correctly. This is ACE, ACE BDF. So that is your LHS. So that proves your associativity. Then existence of multiplicative identity. When you have your B to be non-zero element present in D, then BB will act as, suppose C is non-zero, CC will act as class CC, and A non-zero, AA will act as unit element. Again the same explanation. How can you say that there are too many unit elements in a field F? If you have to have F to be a field, you cannot have too many unit elements, but these are all as classes, they are all equal, so they are the same. So whether you consider BB or AA, when you know them to be A non-zero, B non-zero, and D non-zero, you will have them all to be equal. Because see, when you consider BB element BB, it is related to AB. I mean AA, because BA equals BA, and the same way AD equals DA. So as elements are related, the corresponding equivalence classes must be equal. So in that way we can say that. So that is what here as a note is given. If one is a member of D, then one will be a unit element in F, right? So what we need is one non-zero element, right? Then existence of multiplicative inverse for any AB which is different, should be a non-zero element. Non-zero element should have inverse. That is the condition. So because it is non-zero, we need to mention that it is non-zero. So for that only we have written like this. We cannot simply write AB not equal to 0. We know that 0 element in F is written as this. So to say that it is a non-zero element, this is how we can express. Then its inverse will be BA. So when you multiply them, you will get back. See, we shall see. See, when you have this to be not equal to this, which means your A is non-zero as well as B is non-zero. So when you consider AB into BA, the sequence class, what you get is AB, BA. But that is same as ABAB. And just now we said that A and B are non-zero, and therefore AB non-zero. And not only that, whenever I have B non-zero, we mentioned Whenever A non-zero, A will be unit element. When B non-zero, BB will be unit element. When D non-zero, DD will be unit element. So when AB not equal to 0, AB will be unit element. So when you multiply AB with BA, you are getting unit element, which means that this is inverse of this. So this inverse of AB is nothing but class BA. And commutativity that can be easily established because D is commutative with respect to dot. D is commutative with respect to dot. So using that you have, and from this is very obvious, and that is your RHS. That proves the commutativity with respect to dot. Distributive laws, two laws that you have, it is enough you establish only one. So we have considered this class AB plus class CD dot EF. Class EF should be this into this plus this into this. So we'll consider LHS, simplify, consider RHS, simplify and show both are equal. So LHS, when you consider, it is AD plus BC comma BD and this one. Now you will have to multiply these two. So AD plus BC into E. Thus, now this is ADE plus BCE BDF. Let it be like this. Then go to the RHS. So you have AE BF plus CEDF. So you have this. Now you'll have to by the definition of addition, this into this. So AE into DF plus this into this, BF plus BF into CE, then BF DF. Now, using distributive law, using commutativity, all that you can have, and take out F. So this is what you have. And here F is non-zero. So it comes in the second place. That means F should be non-zero. If it is non-zero, then you can avoid that in the next step and write this. You know the reason behind it. Too many times it is explained earlier. Um, so you have this, and that is your RHS. So distributive law also established. In the same way, you can establish this. So that is not proved. Uh, Now, from all this, we conclude that F under plus and dot is a field. Now, our main proof is to have D to be embedded in F, embedded or embedded. For that, you define a mapping phi from D to F in this way. Any element here, you take it as some A, and let phi take this A to class A1. Now, should we define only in this way? Can it not be defined some other way? Yes, it can be defined in this way also. And in that case, you have to say about x that x is non-zero. But anyhow, this x is equal to a1. That is also explained earlier. Because as elements x being related to the element a1, because this into this is same as this into this, as elements are related, equivalence corresponding equivalence classes must be equal. So whether I write AXX or A1, it is going to be the same. So we can very well have the definition in this way. Now, being defined by S, we have to show that it is well defined, for which you consider two elements in the domain to be the same, say A equals A prime. You consider A1, just replace A by A prime 1, so you have this. But this is nothing but phi of A, and that is phi of A prime. So elements in the domain are equal implies their images to be equal in the codomain, therefore phi is well defined. Now, to prove one-to-one, you have to consider the images to be the same. Phi of A equals phi of A prime. That means this equals this. Because the equivalence classes are equal, the corresponding elements must be related. So we have this. But this is A into 1 equal to 1 into A prime. So that implies A equals A prime. Therefore, phi is 1-to-1. Now, to prove that phi is a homomorphism, we prove that phi of A plus B is phi of A plus phi of B, and phi of A dot B is phi of A dot phi of B. Remember, this plus is the plus in D and dot in D. This plus is plus in F, this dot is dot in F. Now LHS of 1, when you consider it, is a plus b comma 1. That is how it is defined. Mapping phi is defined in this way. Whatever element that you have here, that should come in the first place, 1 in the second. And RHS A1 plus B1. And when you add it, this into this plus this into this. So A into 1 plus 1 into B, then 1 into 1. So you have that to be 1. And this is A plus B. Both being the same, you have LHS is equal to RHS. And in the same way, you have the LHS of the second one, LHS of the second should be same as RHS of the second. So you have phi to be a homomorphism. So because by the definition we have our phi from D to F to be 1-to-1 homomorphism, D is embedded in F. Now the unit element 1 is mapped to phi of 1. That is how 1 is taken to phi of 1. But that is nothing but 1 1. That is nothing but 1 1, which is also a unit element. This is also a unit element in F. Now this F is usually called the field of quotients of D. And in the special case in which D is the ring of integers, the F so constructed is the field of rational numbers. So this AB is treated as A by B. So collection of all A by B with B not equal to 0, we denote that as, this is what F we chose as. And this is nothing but your Q. So when you have D to be Z, the ring of integers, D Z means what will be your F? It is Q, right? So in this way, so that is the reason why we consider integers as a rational number, right? So this is the proof and this is the application, right? Thank you.